Hey, what's up, biochemistry classmates? So today we're going to talk about part 2 to lipid synthesis. Specifically just the last objective. What are eicosanoids and where do they come from? Um, we're going to talk about this and then we're going to transition into applications of eicosanoids. It's going to be really interesting, I think, especially if you're pre-med and you're into medicine. So make sure you stick around for that. Anyways, so what are they? This is straight out of the textbook, this definition. Family of very potent biological signaling molecules, which are fatty acids, that act as short-range messengers. So the really only important thing here is short range, so they affect tissues near them. Um, yeah, so if an eicosanoid is made in your heart, it's going to affect the tissues in your heart and the tissues around your heart, basically. This is different than like a neurotransmitter, right? Which has like kind of long range effects sometimes. Cool, let's keep going. All right, so where do they even come from? In order for us to produce an eicosanoid, we first have to get it from our diet because so plant products, right? Plant products, they have this molecule called linoleate, and it's basically a fat that a lot of plants make, so you can find it in a lot of seeds. And that makes sense, right? Seeds are rich in flavor because they have fat. Um, and so like pumpkin seeds. I drew a walnut here. I don't know. It kind of looks like I don't know. But yeah, pumpkin seeds, sunflower seeds, just all kinds of seeds. But essentially, this linoleate is going to be turned into arachidonate, and this is a very important precursor to a lot of eicosanoids. So today we're going to talk about 4 eicosanoids specifically, and 3 of them have the precursor of arachidonate. So this guy's important, this guy's definitely important, and the way this happens is your linoleate is going to become arachidonate via enzymes found in your smooth endoplasmic reticulum. Yeah, cool, let's keep going. A lot of these eicosanoids are omega fat derivatives. And this is important because it once again reflects that we can't just make these in our body. We have to get the precursors from a different source, right? So, for example, leukotrienes. This is one type of eicosanoid we're going to talk about today. They're omega-6 fatty acid derivatives. And so you might think about your parents, like I know my dad, he takes like this omega-3 fatty acid supplement, and it comes from like fish oil, right? And that's important for him, and it helps his heart because he can't make these omega fats, right? So it's definitely very good to take that supplement, I think, for him. But like when he takes it and he like burps, it's like the most it's so gross. Moving on, let's talk about the specific eicosanoids that are mentioned in our reading. So there's 4 total. The first one is prostaglandins, okay? So we start off with our linoleate and then our smooth ER enzymes. They're going to turn that into our arachidonate. And then this enzyme called prostaglandin H2 synthase, also called COX for short. Sorry. It's going to make this prostaglandin H2. This is abbreviated PGH2 in our book. So yeah, this is one family of eicosanoids, and the one that we're going to be looking at both of these, but there are 2 isozymes, right? So 2 similar enzymes that do slightly different things, COX-1 and COX-2. COX-1 is going to make a series 1 prostaglandin, and COX-2 is going to make a series 2 prostaglandin. Alright, so prostaglandins. So like I said, there are 2 types, right? The first one is a series 1, and it's produced by your COX-1 enzyme. Blah, 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 blah. It's responsible for regulation of secretion of gastric mucin. This gastric mucin is basically like, it basically just protects your GI tract, right, from harmful things like oxidative stress and like all kinds of things. But it basically just protects your insides, your stomach, your intestines, all of it. So that's the first type. The second type is COX-2, and this is responsible for inflammation, pain, and fever during injury and stress. So, um, inflammation, pain, and fever, this sounds like flu-like symptoms to me, right? And we're going to talk about later, right? When you have a fever and you're hurting everywhere, we like to take ibuprofen, right? Or a different type of non-steroidal anti-inflammatory drug. But yeah, so we're going to talk about how that works later. But yeah, so prostaglandin series 1, gastric mucin. Prostaglandin series 2, in response to injury or stress, is going to make some blood vessels inflamed. It's going to make you feel pain, and it's going to raise your temperature. All right. All right, so the second type of eicosanoids. So the first type was prostaglandins, and the second type is going to be thromboxanes, okay? So the pathway to thromboxanes is a lot similar to prostaglandins, except we have one extra step. So you're going to go from linoleate to arachidonate, and from that to PGH2 with COX, right? And then we're going to focus on COX-2 today, and we're going to focus on series 2 thromboxanes. I don't think the textbook mentioned COX-1 thromboxanes, so yeah. Anyways, so your PGH turns into your thromboxanes with the enzyme thromboxane synthase. So what do these guys do? They basically just induce the constriction of your blood vessels, so your blood vessels will tighten up, and this will probably increase your blood pressure, right? And they also induce this platelet aggregation. And if you don't know, platelets are used to clot blood, basically. And so this is what is responsible for blood clots. And that's important, right? Like if you're getting a cut, you want your blood to clot up there so you don't bleed out. This can also be harmful though, right? And things like strokes, right? And heart attacks. And all kinds blood clots are not fun a lot of time. So yeah, thromboxanes, let's keep going here. Okay, so the third type is leukotrienes. Leukotrienes are basically a linear derivative of thromboxanes. So thromboxanes and prostaglandins, they're cyclic. Leukotrienes are going to be linear. They're found in your heart, your brain, your lung, and your spleen. It's basically this oxidase that is found in some enzymes called or this is not an enzyme, but it's important in this molecule, Cytochrome P-450, Cytochrome 450, P-450. And this is what works in a lot of oxidases, oxygenases, and they're essentially important for drug metabolism. So what happens when you take a drug is you oxidize it first, and then from there it continues to break down and detoxify. So this is also derived from arachidonate, and you're going to use a variety of these enzymes called lipooxygenases, and you're going to make this leukotriene. Notice here that PGH2 is not a precursor, but arachidonate still is, okay? So that's one important thing between leukotrienes and thromboxanes and prostaglandins. All right, so the fourth and final eicosanoid we're going to talk about is specialized pro-resolving mediators, or SPMs for short. They're basically just used for removal of debris, microbes, and dead cells. This is important for like regeneration of cells. And so I like to think of these guys like the garbage man of eicosanoids. Yeah. And these guys, they come from essential fatty acids. So arachidonate is not going to be a precursor, but it's still important. It's still in the three other ones, right? There's a whole nother class of like eicosanoids that the textbook doesn't mention, but there are a lot of them. So just quick recap. There were 4 eicosanoids we talked about. Prostaglandins, right? There was type 1 and type 2, or series 1 and series 2. They're responsible for like GI stuff and inflammation, fever, pain. And then we also talk about thromboxanes, right? This is important in blood clotting. And then the third one we talked about were leukotrienes. This is important in drug metabolism, right? And then the last one, these SPMs, they're just going to be the garbage man of the eicosanoids, basically. All right, so our first application. So this is not included in our objectives, but this is pretty cool. I think you should stick around and watch. So aspirin is actually used to inhibit these COX enzymes, and the way it does it is acetylation of a serine residue in the active site of COX-2 enzymes. So I say COX-2 here, but it's actually COX-1 and COX-2, but it sort of targets COX-2 a little bit more. And so what does this lead to, right? So if you remember, COX-2 is responsible for prostaglandin series 2, and that's responsible for pain, fever, and inflammation. So when you take aspirin, it's going to actually reduce some pain, it's going to reduce your fever, and reduce inflammation. Pretty simple, right? Also, ibuprofen, right? This is an NSAID, and NSAID stands for non-steroidal, because this is not a steroid, anti-inflammatory drug. Anti-inflammatory, so remember PGH2 series 2 is responsible for inflammation. This guy's going to inhibit in a similar way to aspirin, and it works very similarly. So when we get sick, right, with a cold or a flu or something, we like to take ibuprofen, and this reduces our fever. We feel like we're in less pain, and yeah, it just works really well. So what about COX-1? Aspirin and ibuprofen, they actually also inhibit COX-1. Like, these isozymes are very similar, right? And so, like, what are the side effects of this? So remember we said COX-1 was responsible for prostaglandin series 1, which was responsible for gastric mucin secretion. So sometimes you'll get like abdominal pain if you take too much ibuprofen. And this has actually happened to me sometimes. Like, if I wake up and especially if I haven't eaten anything all day, I haven't produced that mucin that protects my GI linings. And so if I take like Advil, for example, I can get like pretty bad stomach aches if I haven't eaten yet. And my dad is similar to this, so like he will not take Advil even if he has a lot of pain in the morning until he's eaten something. So I thought that was cool. Moving on. More application, more yay. So what else can be affected by aspirin? So prostaglandins, we got that out of the way, but also thromboxanes, right? So thromboxane follows the PGH2 with the thromboxane synthase, remember? So if you're inhibiting up there, you're also going to inhibit thromboxane production. And what did we say this guy was responsible for? This was responsible for platelet aggregation, right? And so platelet aggregation is important because if you get like cut, for example, you want to stop that bleeding. But it can also stab you in the back. So things like stroke, right? So like a clot in your brain, or like a heart attack, a clot in your heart, right? These things called pulmonary embolisms. It's a blood clot in your pulmonary artery, or like deep vein thrombosis. This is like a blood clot in your extremities, right? These are going to stop blood supply to your brain, your heart, right? Your lungs, your legs, your arms. And that's not good. We want to get nutrients. We want to get oxygen to all of these tissue, right? And so how is aspirin used to prevent some medical conditions? So I scribe at a hospital, and one of the medications that a lot of the patients take is baby aspirin. So like a small dosage of aspirin, basically, right? And they take it every day, and these people aren't necessarily unhealthy, but they have like high hypertension sometimes, or high cholesterol, or pre-existing heart conditions, and basically they're at risk for all of these things, right? These blood clots and these pulmonary embolisms and strokes and heart attacks, they're at risk, at higher risk than a lot of us, right? And so they take baby aspirin, and what that's going to do is reduce the amount of thromboxanes that are made, and so it's going to be less platelet aggregation, right? And then, so it basically reduces the risk of all of these blood clotting conditions, right? Also, aspirin works in a way that it opens up your blood vessels. So thromboxanes, not only do they do platelet aggregation, they're also responsible for vessel constricting, right? So if you think about it, if your vessels are more open, right, there's less likely of a chance for a clot to form. So yeah, baby aspirin, pretty important. The last application, even more application, even more yay. So the last thing we're going to talk about is this Cytochrome P-450. And this is a molecule, right, found in a lot of oxidation reduction reaction related enzymes. So like oxygenase, but also you could talk about like oxidase as well. But essentially, these guys are important in drug detoxification, right? So when you take a drug, specifically we're going to talk about like barbiturates and alcohol, but say you like drink some alcohol, this guy's going to be important in oxidating that alcohol, and that oxidated version of your alcohol is going to go through a bunch of other pathways and basically detoxify the harmful effects of these drugs that we put in our body, right? So let's talk about barbiturates and alcohol. Barbiturates and alcohol, these are both drugs and they fall under the class of depressants. Some of you guys may know this if you're like studying for the MCAT. They talk about it in the psychology section, I think. Yeah, but anyway, so barbiturates, what are these? This is a depressant, like I said, and it's used to treat things like anxiety and like seizures and insomnia, and those are the major ones, I think. But basically, what does a depressant do? It's going to affect your central nervous system, and it's going to depress it. It's going to suppress its activity, and so you feel more relaxed, right? And you're basically going to slow your central nervous system down. So like, for example, seizures, right? So barbiturates are used as a anticonvulsant sometimes. Seizures is an overstimulation of your brain, so an overstimulation of your central nervous system, and this is going to depress it. So it's gonna help with seizures, right? And also alcohol, right? Alcohol is also a depressant. It works not in the same way, not in the same pathway, but it has similar effects, right? So should we ever mix barbiturates and alcohol? And the answer is no. Definitely not, right? Def not. Heck to the no. And why not? The reason is we only have so much of this cytochrome P-450, okay? So if we have like, if I had anxiety, for example, right, or insomnia, and I was prescribed barbiturates, it is very, very, very important that my doctor tells me not to drink any alcohol. Because essentially what's going to happen is I have limited molecules of cytochrome P-450, right? And so some of it's going to be used to detoxify the barbiturates I'm taking for my anxiety or insomnia or seizures or whatever it may be. And then some of it's going to be used to detoxify the alcohol that I had been drinking, right? And eventually all of this is going to be used. But you're not going to feel very drunk. Like even if you drink a little bit, right? A lot of this is being used to detoxify your barbiturates. So even if you don't drink a lot of alcohol, you're going to have a lot acting on your central nervous system because a lot of it is not being detoxified. So essentially what happens is you can overdose. And so if you're on this barbiturate and you go out drinking and you drink like five beers, 6 beers, like not too much, but you know, a moderate amount, you can overload the depression of your central nervous system, and what happens is you get you slow your breathing down, and then eventually you stop breathing, and then you don't get oxygen to your brain and your other body parts, and you die. So this is very dangerous, this combination. There are other depressants as well, right? So like benzodiazepates, I think is another one. So you don't drink alcohol with those as well. Um, so the final application thing is like a tolerance to drugs. So I'm studying for my MCAT right now, and I was reading about the tolerance section, and it said that it's because you lose receptors in your brain, or like in your brain, and so you need more of a drug to get the same stimulation. Um, it also works in this way as well, this cytochrome P-450 way. So in addition to your receptors maybe not working as well, or you're not reuptaking these neurotransmitters in your brain, the cytochrome P-450, the more you take a drug, so like if you're an alcoholic and you drink alcohol every day, the more cytochrome P-450 you're going to have, so the more efficient you're going to be at breaking down these drugs. And so you're going to create this tolerance, right? So in addition to the stuff that's happening in your nervous system, additionally, like these enzymes that are responsible for metabolizing these drugs, they're also going to be affected. So I thought that was pretty cool. Now, one last thing, like withdrawals, why not, right? So with withdrawals, right? So like you're gonna have, say you've been taking barbiturates for a while, right? And you have a high level of cytochrome P-450 because you need a lot of it to break this drug down, right? If you stop taking this, right? So what's gonna happen basically? You're gonna have these withdrawal effects, like as if you're overstimulating your central nervous system. Does that kind of make sense? Because you have a lot of this guy, and now you no longer have any of this guy, and so your central nervous system is going to be overstimulated. And so one of the withdrawal symptoms you see with alcoholics is seizures, right? Because maybe they have a lot of this guy, right? And then they stop drinking, and then their central nervous system gets overstimulated, and then the result is a seizure. Cool. Little application for you guys. So that's the end of the first objective set. I am working on the second objective set. What is it, like complex lipids or something? So I will have that out soon. Thank you guys. Hope this was helpful.